Alright, so a bit while back, we got hit with COVID-19, the pandemic. And obviously it wasn't a good time and we're still recovering from it. But when I thought back to COVID, I realized that we shifted a lot as a world and as a society. I mean, societally, we spent a lot more time on our laptops, on our phones, on our computers, on our screens as a whole. And companies honestly had to shift virtually, so we saw a huge rise in platforms like Zoom, Google Meet, Microsoft Teams, and anything and everything related to web calling. Now, aside from just that, a lot of other industries faced changes during COVID, including healthcare. I mean, the rise of telemedicine and remote monitoring became huge during COVID because you wanted to reduce the amount that you were going outside, especially to places with a high density of COVID patients. So, as I got deeper into that, I realized that different tech hubs and different tech companies like Google and Apple even entered this market of healthcare and telemedicine during this time. And they created contact tracing. So essentially, you'd be able to tell who could possibly be affected by COVID if one person had COVID. Now, the way that they did this, they made this whole app where you'd be able to do contact tracing. And I got super interested in it, and I've been recently diving deeper into AI, specifically machine learning, and I decided to create my own contact tracing platform. So in this video, I'm going to go through what contact tracing actually is, why it's useful, and then go through my code of how I built it out and give a quick live demo. And if you'd like to build it with me as well, you can check out the dataset I used in the description. It's a JSON file. And you can also check out the GitHub repository, which will be in the description. But let's get into what contact tracing actually is and why it's useful. Alright, so contact tracing is a pretty basic concept to follow. But if you think about COVID as a whole, there's multiple ways that we can try to stop the spreading of COVID. So obviously we had lockdowns, which were when countries would basically some countries would put a curfew on when you could not go out beyond that timing. And lockdowns would basically be you don't really go outside for anything other than necessary things like grocery or going to the doctors. So lockdowns was one way. Another way was quarantine. So if you found out you had COVID, you'd be staying in your house for 14 days, and I think it went down to 5 days after COVID settled down a little bit more. But another way was obviously drug testing and trying to build and make out the vaccine, which we did in roughly a year or so. And the final one was through contact tracing. So contact tracing is trying to identify other people that might have been exposed to COVID from one central carrier. So carrier is the person that actually holds COVID. So let's say that it's person X. Person X might be holding COVID-19 virus in their body right now, but let's just say that they don't know that they have COVID. So what will happen is this person travels a lot, obviously, right? We can pretend that person X works in Toronto and they take the subway to get to work every single day. Now, there's a lot of different points of contact. You know, they might be taking a bus to the subway station, right? That's them at one point in time. At another point in time, they're in the actual subway. At another point in time, they're tapping their Presto to get off of the subway. Then they're walking down the street. Then they're actually going in the elevator of their office. Then they're in their office. They're going to the bathroom. They're going to the general sitting area. Then they're doing the entire thing on the way back. So you can see that anyone that has COVID, anyone in general, we move around a lot. And so that one person, let's say that's person X, is moving around doing this entire thing in just 1 day span. They are coming in contact with a lot of people. And so what contact tracing does is it essentially uses a density-based or partitioning-based cluster model. It depends on which one you're using. I decided to use a density-based one, which is DBSCAN. And it will basically determine where that person goes. It's their latitude and longitude, so their geographical area, at different timestamps, and then identify people that could have been in close contact and create a cluster of them. When they create a cluster, basically then if that person is diagnosed as positive, then they're going to go through that list of people and then see who might have been identified as positive as well, who could have been affected, and then they can go get tested out. And it will basically have better use of treatment and better use of testing, but also prevent the spread even further because then you're able to tell I might have been in close contact with someone who had COVID. So that's the basis of how contact tracing works. And now I'm going to go through how I actually use DBSCAN to go through this entire process of actually contact tracing 10 different people. Okay, so I want to start by actually showing you the data and how this all looks. So every single person that we have on this contact tracing algorithm, we have 10 people, and each of them have 10 instances. So each person is essentially an ID. So Alice, for example, is our first ID, and this is a unique person. So Alice has 10 instances, which means she has 10 records. So she has 10 different timestamps, as you can see here. Like we have Alice for these first 10, right? So Alice has 10 different timestamps, and then she has 10 different latitudes and 10 different longitudes. And the intention behind this is to try to mimic how someone would move in real life. So when I talked about person X, and I was saying, person X would go in, the bus to go to the subway, and they'd go in the subway, and they would tap their Presto card, and then they'd go in the elevator, and then they would go in their office, right? They're working in all these different locations, so a certain person moves around a lot. And these 10 instances are to show that a person is going to move around a lot. So we have 10 different records per person. Each of them have their ID, which is their name, their timestamp, which is what date and time they were actually doing this, and each timestamp per person is 1 hour apart, so 3,600 seconds. And then we have the latitude and longitude, which is going to give them 1 point. So in every single scatter plot or any single plot you'll see, the x-axis is always going to be the latitude and the y-axis is always going to be the longitude. And when they come together, they're going to make their 1 point. So this is essentially going to be 1 point for Alice. This is going to be another point for Alice. And so we're going to keep going like that for all the 10 people. And they have, I think, a minimum of 10 instances. They might have more. So that's how the data set actually looks, and it's quite long. So you have Bob, you have Carol, you got David, and so it's the same thing for all of them. Okay, so now I'm going to go through the actual code and how it works. This is all done on a Jupyter notebook because it has all the necessary libraries that we need for Python. And so the first part is essentially just importing all of the libraries. So there's a few normal ones here, but we use pandas for data manipulation because you're going to see that we need to actually see all the data. So we use pandas for that and refer to that as PD. And then we have the matplot library and then Seaborn for data visualization because we have to plot a lot of different graphs because it's how you actually make the clusters. And then we also have to import the DBSCAN one. And as I go through this, I'm just going to run each block of code so that it can run cohesively and I can do a quick live demo at the end. So the next part of this is essentially reading the JSON file. So it is a mock created data set from JSON. And all of this is written in an article, which you can check in the description as well because it has all the parameters for actually creating the mock data set. So all of this is read through pandas, and you just read the JSON file, which is the data set I previously showed, and you read it and add it all onto the data frame. So every time we want to refer to the data, we don't have to refer to, like data frame or like this entire thing. We can just refer to DF. And so after you read that, the next part is essentially printing all the necessary information for the data frame. So this part is super important because you want to make sure you have the right content. So we have 241 entries, which means there's 241 different names and everything like that. So this is what every single data part looks like. So for every instance, we have 4 columns. So you have your ID, which is a person's name. You have your timestamp, which is the date, the month, the year, and then the actual hour, minute, second. And that is all has to be daytime. And then you have the latitude and longitude, which have to be in float. If they're in string, they're not going to read as latitude and longitude. And I had a huge issue with this. So you have to make sure that they're in float point numbers. And these are all the types, and then this is just the memory usage. So the second part of this is essentially calling back on the data frame function and describing it. So this essentially gives all of the extra information about each instance. So I have the count, the mean, all of these has to do with latitude and longitude. And if you look at the count, it says 241, and here you also have 241. So you just need to make sure it's cohesive. And then you have your minimum and maximum. And this is also important to notice. You have your 25%, 50%, and 75%. And this is the amount or the number of that data that is within 25% of the entire data. And you're going to see this when we plot the box plots, which I'll explain a little bit more later. But you want to just keep in these portions in mind because there's different portions of the data. And then the next portion of this is essentially calling back on the data frame and returning the head. So this is the first 5 rows from the data frame, and when we looked at the data set here, right, we have 5 things of Alice. So these 5 instances, you can again see the timestamp has year, month, date, hour, minute, second, their latitude and their longitude, and then you have Alice, and here are just the first 5 rows. So the next part is we're done kind of seeing what each instance has, but now it's how many instances do we have. So then we call back on data frame and we look at ID and we call the unique function. And unique is going to return back the array of all possible IDs or all possible people in the data frame. So in this case, we've got like Alice, Bob, Carol, David, all these names, and these are all, I think there's 10 of these. So these are all the people that we're going to be looking for. And then this next part is essentially, now we're looking at the EDA, or the exploratory data analysis. So this section of the entire code is all of the graphs, and not all of them, but most of them, and this is just different ways of displaying the data so we can better understand it. Okay, so for the next EDA section, we're going to start by actually making a scatter plot about the latitude and longitude compared to the ID, or the person that we're actually testing for. So in this case, we have our plot figure, which is just how big it's going to be, and you can change the side accordingly to what you desire. And then we have our scatter plot, which is used through the Seaborn library, and our x-axis is our latitude, y-axis is the longitude. The data comes from our data frame, which is again calling on the data, we just use it as df. And then our hue is essentially what colors are you encoding onto your legend. So this is how the scatter plot looks when you run it. So it's already run, but if we want to run it again, this is how it would turn out to be. And so again, latitude, longitude, the numbers on the scale just come from the data, and our hue is this legend. So each of them, all the 10 different IDs with different instances, have different colors. So let's say we're looking at Alice. Alice is this deep blue color, is her color, okay? So she's here, she's over here, 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 here. There's a lot of Alices, right? And this is essentially mimicking how she would move in real life, because in real life, you're moving different latitudes and longitudes at different times. So after we do that, we decided to, still use the same data set, still use the same latitude, longitude, but just do it in a joint plot instead. And a joint plot is just another Seaborn plot that you can make. Then down here, we decided to use box plots, and these are actually pretty interesting. So box plots still come from Seaborn, and we have two different ones. So this first one is comparing the latitude in correlation to the ID, or the name, rather than the latitude and the longitude. So the data again comes from df, the palette is just what colors you want. So over here, let's take a look at Alice to explain how to actually read a box plot. So this middle line is essentially the median of all of her latitudes. This top line is, they're known as quartiles. So that top quartile is where 75% of the data actually falls under. And this lower quartile, known as the first quartile, is where 25% of the data can fall up to. So that's how you read, so that data is specifically regarding the latitudes. And then these are known as the whiskers. So the whiskers of the box plots are essentially the minimum, so the lowest value that this goes up to, and the maximum. But a lot of the latitudes are still in this like blue area for Alice and for all of them. And then these little dots that you have outside are any outliers. So in this case, Alice has one outlier. And when I was talking about the 25% and 75%, if we go back to the data, what I was telling you guys to keep in mind, over here you have these numbers, right? Like her latitude 25% is about 12.9. And so if we're looking up to it, about 25% of our data falls up to this 12.9 part, right? So that's kind of how it's graphed and how to read the box plots. And so we have the exact same thing just with the longitudes and the IDs over here. Alright, so this next portion is actually us defining the model, which is the DBSCAN model. Alright, so we're getting closer by the minute, but this next portion is actually defining the model. So we know that it's a clustering model, and the basis of a clustering model is it's going to take points that are similar and put them together into one grouping. And then points that are different are going to be in different clusters. And that's the entire basis of it. And so DBSCAN is a density-based clustering algorithm. And so what it does is based on similar characteristics, it clusters things together. So in this case, you always have to define your EPS, which is the minimum distance that is needed to show that this is almost like a distance of danger. So in this case, we're using 0.0018288, which is 6 feet in kilometers. So according to the health authorities, anything below 6 feet is considered of danger. So that's when you actually want to keep in mind that these people are going to be, if they come in contact, then they have a risk of transmission of COVID. So we always define that. And then our model is our DBSCAN model. And then our metric is known as Haversine. So the metric is essentially the distance between two data points to also be known as similar. So they're not clustered together at this point, but it's essentially known as similar, and we need these to actually identify the distances between people. And Haversine is essentially a type of metric which you can use, and it essentially uses a circle to cluster or define these as similar because it has its own distance between data points. And then you also, again, have your latitude and longitude, and this is essentially just defining the model in the beginning. So our next point is actually, again, plotting. So again, making another scatter plot with latitude and longitude as the x and y axes, as defined here. But instead, your who, so instead of having them as your IDs only, they're going to be your clusters. So you can see them here. So this is a scatter plot, right? We got our latitude, we got our longitude. These are all of our clusters. So now, if we're looking at, what's a distinct color? Let's look at like this lime green cluster, which might be, I'm assuming, like cluster 8, right? This is a cluster. It's a ton of points. It's not just known as one point, right? And we can see there's a lot of cluster -1. There's a lot of these like random pink clusters. And we actually want to get rid of those because those are known as noise. So if you're running this is essentially like any of those clusters in noise. Those are irrelevant. Those aren't really significant to us. But they are hindering our ability to actually interpret what the scatter plot is saying. So instead, we're going to essentially just get rid of them. And if you run that, you're going to get a much cleaner scatter plot of all of the things that we actually need. And if you look at the legend, there's no -1 anymore. So this is essentially all the clusters that actually matter. So these clusters here are capable of transmission of COVID next to each other. And that's kind of just what this all means. And when you go to the next one, this is essentially actually testing out the model. And the way that you do this is when you call out get infected names, you're able to then go through the data set again. You are going to relate it back to your EPS, which in this case was our 0.0018288 kilometers. And then you're running it back through your model and you're having a cluster. This is the exact same thing as over here. And now we're actually saying that the names are going to be displayed in an array. And when you kind of go through this code, so if we're saying that the data or the certain ID in this data frame, if it is in the input names, we're going to pass it, otherwise we're going to append it. And so the infected names are going to be coming into a cluster. And if the cluster is -1, we're saying that this is only going to run if the cluster is not -1. So if it's not noise, right? So we need to make sure that it's any cluster between 0, so cluster 0 to cluster 28, because we form 29 clusters. So after that, we're essentially saying that, we're just going to go through this line of code, and then you're going to return the infected names. And this is how it works, and now we're going to do a quick demo. Okay, so now we're on to the live demo part, which is, like I mentioned, if you call get infected names and put a name in the array, which is what we want, then you'd be able to determine who else would be affected, and then the health authorities can contact that person. So we've already done 3 examples here. Let's do another one. So let's say get infected names, and we'll do it for Heidi, I think was one of the names. And if we run it, you're able to then see that David and Judy could possibly have been in contact with Heidi. And so if you looked at David, then Heidi's also there. Now let's say we do get infected names Judy, because she's in quite a few. So we run that. Oh, error. We run that, you can then see Heidi and Alice. So when you look at Alice, Judy is the infected name person, and then when you look at Heidi, Judy's also infected name. So obviously when you call on Judy, Heidi and Alice are going to pop up. So that is essentially how the code works. Alright, and just like that, that is essentially how the contact tracing algorithm with DBSCAN actually works. Now, although this is a great use to actually help prevent the spread of COVID, it still has its cons. And some of the cons are actually that it's very difficult to implement this. So the reason behind that is because you need a lot of data for this. And in my case, we have 10 different instances per person. So you have 10 different records per person in one day. But really, if we wanted very accurate records, you maybe need 16 instances, maybe if we're saying that someone is sleeping for 8 hours, right? If you need 16 instances per person every single day, you need a lot of data. And we got this through GPS data. Even though this was mock data generated, the actual data would be generated through GPS, but it's also a lot to collect that data. And then there's also a lot of false positives that could actually arise from this, because you could say that, yeah, Judy came in contact with Heidi, so they possibly have a chance of, having COVID transmission. But really, you don't know how long they could have been in contact for, because the timestamps are an hour, apart, right? And then aside from that, you also don't know if they were really that close to each other. Like, sure, maybe they were at a different distance at certain points, right? So it's difficult to actually know the accuracy of this. However, it's still a great use case for a wide-scale population method, and great for public health, but not really very personalized to the person. But overall, have any feedback, let me know. I hope you enjoyed, and I hope you learned a little bit more about contact tracing and how we can actually use this for pandemics and also other transmittable diseases. Until next time.